Here's another work energy theorem problem. The picture's drawn up on the board. We have our skier going down the hill and going to end up at the bottom of the hill. The forces on the skier are force of gravity parallel going down the hill, force of friction going back up the hill, and an initial speed of 3 meters per second. Those are the same forces acting on the skier down here when their final speed is 16 meters per second. The angle of the hill is 25 degrees. We know the mass of the skier is 58 kilograms, and we know that the length of the hill is 60 meters. From here, what we can do is actually solve for the force of friction acting on the skier using the work energy theorem, and here's how we do it. The work energy theorem, hopefully you remember, is the net work done on the skier in this case, or anything, is equal to the change in kinetic energy of the object. Well, what is net work? Net work is all the work done by any forces acting on the skier that are acting in the direction that it's moving. Gravity parallel is pulling down the hill in the direction of the motion, and force friction is going up the hill in the exact opposite direction of the motion. Both of those are doing work on the skier. So here's what that is going to look like. First, we'll do gravity parallel, which is going to be negative work. Or sorry, positive work. Force of friction does negative work because it's going in the other direction. So first we got positive work, which is force of gravity parallel multiplied by the distance that the skier slides down the hill. Then we've got the force of friction, which is negative work, which is why there's a minus sign there, also times the distance. All that's going to equal the change in kinetic energy. Well, that is final kinetic energy minus initial kinetic energy. So when I expand that equation a little bit more, my left side remains unchanged. I've still got gravity parallel times the distance minus force of friction times the distance. And that's going to be equal to the change in kinetic energy. And that change in kinetic energy, we just use our equation for kinetic energy, which is 1/2 mass times v squared. We're going to have the final velocity here because it's final kinetic energy. So that's Vf squared minus the initial kinetic energy, which is 1/2 m times v naught squared. So what is this question asking for? This question is asking for us to find the force of friction. That's what we want here. That's what the equation is saying. Hey, what is the force of friction if this person only was able to accelerate to 16 meters per second? So we're going to solve for the force of friction, and we're going to do that first by subtracting this term, gravity parallel times distance. We're going to subtract that over to the right side, and this is what my equation will look like as a result of that. Don't lose your negative sign in front of the force of friction times distance. That's still there. That minus sign still counts. And that's going to equal 1/2 times m Vf squared minus 1/2 times the mass times v naught squared. And now we are subtracting that force of gravity parallel times the distance. Now what we need to do is we need to divide the d that's hanging out with this force of friction here, and we need to get rid of this negative sign. So what I'm going to do is I'm going to divide by negative d, and then I'm just going to put that in the denominator on this right side of my equal sign. And what that's going to look like is I'm going to divide real large negative d. And then over here on this side, what that means is my d is going to go away because I just divided it out. And so is my negative sign because I just divided that out too. What we can do now is we can finish this up and plug in all of our numbers. So we're going to have the force of friction equaling the 1/2 times the mass, which is 58 kilograms, times the final velocity, which was 16 meters per second, and we square it, minus 1/2 times the mass again, which is still 58 kilograms, times the initial speed, which was 3 meters per second, minus force of gravity parallel. We have an equation for force of gravity parallel. It was the sine of 25 degrees times m times g. The mass is still 58 kilograms. I have to go in here to the blue, or write it in yellow then so it shows up really well, times the 9.8 meters per second squared, because that's just force of gravity parallel, is sine of the angle times mass times 9.8, times the distance, which I'm not going to write in blue because we're already on blue, and that distance was 60 meters. Just about out of room there. And we're going to divide all of that stuff. All that's divided by negative 60 meters. And when I plug all of that into my calculator, every single thing, what I end up with is an answer that the force of friction has got to be 120.8 newtons.